So now let us see Rosenmund reduction. Here Rosenmund reduction is a catalytic hydrogenation reaction where we will be getting our aldehyde as a product from acyl chloride. So here first we will be taking our acyl chloride. So when acyl chloride is undergoing catalytic hydrogenation, we will be getting aldehyde in the presence of catalyst. It is a partially deactivated palladium catalyst, which is PDBS4. Why are we deactivating palladium catalyst? Is only to prevent the unwanted reductions. Unwanted reduction in the sense, as we know, we can see our product here is aldehyde. So this aldehyde, it can again further convert into primary alcohol, which again will convert into our alkenes. So in order to prevent that further reductions, we are using partially deactivated palladium catalyst. So how are we deactivating it? By using BaSO4. We are going to poison palladium catalyst by using BaSO4, converting into a partially deactivated palladium catalyst. So PDBaSO4 is called our Linda's catalyst. So here, if at all the R group that we are taking here is an aliphatic group, then we will be using a solvent, anhydrous solvent, which is our toluene, and then we are going to reflex the reaction where we will be getting our aldehyde. So aliphatic in the sense it can be CH3, it can be C2H5, and all the straight chain carbons you can take here. Aliphatic, they are aliphatic. And now when it comes to aromatic, when the R group is aromatic, like for example you can take C6H5 as well as naphthalene. Okay, so in this case we will be using the solvent is quinoline plus S8 polyatomic sulfur. So quinoline plus S8 and in the presence of xylene, and then on reflex we will be getting our aromatic aldehyde over here. So why are we using all these purely anhydrous solvents, which are toluene, quinoline in the sense? Only to avoid the formation of byproducts. Byproducts in the sense again our unwanted reduction. The products that are obtained, which are a primary alcohol as well as alkenes. So in order to prevent the formation of all those byproducts, the two main conditions that we need to follow while undergoing Rosenmund reduction is, first we need to use partially deactivated palladium catalyst over here, and then we need to do this reaction under purely anhydrous solvents by using purely anhydrous solvents, which are a toluene as well as quinoline. Based on the compound R, based on the alkyl group R, we will be using the solvents. Now let us see the mechanism for this reaction. So first here this is acyl chloride. So this acyl chloride, it reacts in the presence of catalyst, Lindlar's catalyst. It will give us this compound where palladium is being introduced between carbon and chlorine. So how are we getting introduced? How is the palladium getting introduced in the sense? First, chlorine, as we know, it is more electronegative. It will take the electrons from carbon. Chlorine here will get a negative charge. Now then carbon here will get a positive charge. So palladium will share the bond with the carbon by donating the electrons. Then palladium here will get a positive charge. Then the negatively charged chlorine will share the electrons, which is having extra electrons, and will give us this compound. Now here we are going to pass H2 gas. H2 gas in the sense it gives one hydride ion, which is H minus. Okay, so this is hydride ion H minus and a proton. Here chlorine, as you know, it is electronegative. It will take the electrons from palladium. It will come out as Cl minus. So H plus and Cl minus, they are removed as HCl. They come out as HCl. And then here palladium will get a positive charge now. Now palladium will take the electrons from carbon. Palladium is eliminated. Here carbonyl group will get a positive charge. Carbon here will get a positive charge. Now the hydride which is formed here will attack at this site and will give us our aldehyde. So this is the reaction for mechanism for Rosenmund reduction. If at all we are not doing this reaction in the presence of solvents, then we will get to see formation of the byproducts. So what are they? Again, in the presence of catalyst, Lindlar's catalyst, we are going to pass hydrogen gas. So what happens here? Oxygen, as it is an electronegative atom, it will take the electrons from carbon, leaving carbon positively charged, and oxygen here will get a negative charge. Now here in H2 gas, I already told you here, one will be getting an hydride ion and a proton. So this proton will form a bond with the negatively charged oxygen and will give us a hydroxy group over here. Here carbon will get a positive charge now. Now to this positive charge, again the hydride ion, it will attack at this side, giving us a primary alcohol. So aldehyde will give us primary alcohol. In the same way, if we take ketones, for example, in some other reaction, if there is a ketone, ketones will give secondary alcohol. But in Rosenmund reaction, we are going to take only acyl chloride, okay? We are not going to take any other compound. So if at all, if there are any chances of getting taking a ketone, then you will be getting a secondary alcohol. So now here aldehyde gave primary alcohol, again further reduction taking place in the presence of Lindlar's catalyst, hydrogen gas is passed. Here water molecule is eliminated. How it is eliminated? First hydroxy group, it will come out, it will take the electrons from carbon OH minus, and from H2 we know that we will get a hydride ion as well as a proton. So proton and OH minus, they are eliminating in the form of water molecule. So here our CH2 plus, carbon will get a positive charge. Now to this positive charge, our hydride ion will attack, giving us our alkane. So in order to prevent the formation of these byproducts, which are alkane and primary alcohol, we will be doing this reaction in purely anhydrous solvents. Okay, so only to prevent the formation of byproducts, we are going to use these compounds, and our final product which we will be getting after following all these conditions is our aldehyde, which can be aliphatic aldehyde or aromatic aldehyde. Now let us see example, okay, two examples where we will be getting to see the usage of Rosenmund reduction. So first is the conversion of acetyl chloride to acetaldehyde, as I said, by using Lindlar's catalyst and by passing hydrogen gas. So here CH3, the R group is aliphatic. So as it is aliphatic, the solvent which we are using is our toluene, and then we will reflex the reaction, we will be getting our acetaldehyde. Now in the second example, you will be getting to see the usage of an aromatic compound, which is naphthalene. So the whole compound is called naphthoyl chloride, and this is alpha beta, you can even say beta naphthoyl chloride, or 1, and this is 2. So you can even say 2 naphthoyl chloride in the presence of Lindlar's catalyst by passing hydrogen gas, in the presence of purely anhydrous solvents, which are quinoline plus polyatomic atom sulfur S8, okay, xylene, and on reflex we will get 2 naphthaldehyde. So here we are getting an aldehyde group, C double bond or H. This can be 2 naphthaldehyde, or you can even say beta naphthaldehyde. So this is Rosenmund reduction.